So we're going to move on to Chapter 8, which is going to look at some more applications of trigonometry. But first, we're going to talk about some new concepts called vectors. Now, most things we've seen in the world are what are called scalars, and scalars are just the measure, the magnitude of a quantity. So basically, how big or how much of something there is. So if I go to the store, maybe I decide that I want to buy 12 pounds of sugar. So that would be a magnitude, it's how much. So the difference between a scalar, when you're just measuring something, and a vector is not only how much something is, so it measures the magnitude, so how big something is, but also the direction. So instead of just being something that's stagnant, that you're just measuring, it's actually something that has a magnitude, an amount in a specific direction in space. So a lot of times this is used to talk about force, because you can pull force in a certain way. Sometimes it's talked about speed and velocity and direction while driving or moving. So sometimes you could say something is being pulled at with 50 pounds of force. We could say 50 degrees east of north. And what that would mean is if I have an object, let's say this is my weight, someone is going to pull 50 degrees east of north. So if here's due north, here's 50, and it's with 50 pounds of force. Now we generally denote vectors with simply a ray. So it starts here and goes here. So we would call this the tail and this the head of the vector. So it's almost like this force is starting here and you're pulling it to a 50-pound thing. Now we talk about magnitude. Magnitude is how much. The magnitude in a vector is simply just how long it is. So the longer the vector is, the more magnitude it has. So if you're pulling at 60, that's going to be longer than if you're pulling at 50. So vectors have magnitude or length, and they have direction. So when we start to actually try to figure out how to talk about these vectors, in one way we'll talk about them is using what are called unit vectors. So unit vectors are just going to be vectors of length 1. So if it's length 1, that means it's magnitude 1, pointing along a positive axis. Now there are only two positive axes for us, the x and y axis. So we give names to each of those specifically. So if we have a vector I, that is a unit vector along the x-axis. So in this picture here, you can see this would be vector I right here. And then vector j, which we make a bold letter kind of going in that direction, is a unit vector along the y-axis. So it'll look something like this. Why this is important is you'll see we can actually define any vector that we have in terms of this vector I and this vector j. So even if it's slanted or going different directions, I can still make it denoted with this I and with this j. And we'll see how that works here in a second. Okay, if I look at a vector, let's say I have a vector, and let's say I start it at the origin, which most of our vectors like to start there. So sometimes we like to write this vector in what's called component form. Now component form, we're going to really just try to figure out how far this vector is and how far this vector is. Because to make this vector, you have to go over the x and up the y to get to this position here. So in a component form of a vector, what we're trying to do is we're trying to name the vector by its x component. So how far O you have to go. and its y component. So there's a certain amount over you have to go and a certain amount up you have to go to define this vector, and we call those the components. Now there's a couple ways to do that, and let's look at this first example. So if you look here, the x component appears to just be 1, and the y component appears to be -3. So there are two ways to write this vector. One is with these kind of pointy brackets, and we say 1, -3, almost like an ordered pair for this last thing, assumably that this vector starts at the origin. The other way to write it is in terms of unit vectors. Remember, each unit vector on the x-axis is called I, and each unit vector on the y-axis is called j. So another way to write this, besides the 1, -3, would be 1i minus 3j. Because if I take a vector of I and 3 vectors of j and I subtract it, I should get this vector I see here in this picture. So let's look at this next vector putting in component form. Now this one is interesting because this one does not start at the origin. This one starts over here and goes this way. Now you can move this vector or you can still do the same thing. We could think the y component is going this way, so it's going from 4 to -1. So it's going down 5j because it's going down in the y direction. And then it's going left this distance. So that distance is going to be from 4 to -4. That's going to be -8i. So this vector is going to be -8i minus 5j, or -8, -5. Some other people would say, well, you could just take these points, which are 4, 4 for the tail, and this would be -4, -1 for the head. And if I subtract those points, if I do the first one, which is 4, or the second one, which is -4 minus the first one, which is 4, and then the second one, -1 minus the first one, then I'll get the same thing. Because anytime you're finding distance, it's always the second minus the first to see where you've gone. So either way is fine. You can just kind of count boxes, or you can do the subtraction when you have 2 points. And this is mainly when you have a vector that doesn't start at the origin. Everything we're really going to look at, we want vectors to start at the origin. Now, a couple really important things we're going to want to know about vectors. We're going to know what the magnitude is, and we're going to want to know what the direction of the vector is. Now, for the magnitude, remember, is going to be the length of the vector, how long it is. And let's say we're given vector A. We write the magnitude in double bars. So when you do the double bars, you get something like this is for magnitude. Now, if I think of this vector, let's just put it in quadrant 1, makes it pretty simple. Then the length is the magnitude is this distance here. I know this is the x component, and I can translate this being the y component. Well, really, you have a right triangle, so you can use Pythagorean theorem. So really, the relationship we can form is the magnitude is squared is equal to the x component squared. And when I write a sub x, that's also a way to represent the x component of the vector, plus a sub y squared. So if you have it, you really just have a Pythagorean theorem. As far as direction we're typically going to think of as an angle in the coordinate plane. So the direction of a vector is going to be the angle that's formed by the vector. Now, this has a really interesting property, because when we do this vector, it doesn't always give us the angle we want. But so what we know is we know the reference angle, theta of the reference angle. If I look at this triangle, I know the tangent of theta equals y over x, opposite over adjacent. So the reference angle is going to be found by the inverse tangent of y over x. Now, once you have your reference angle, we'll have to do a little bit of thinking and try to figure out where exactly this is in the coordinate plane. But essentially, this is how we'll start finding the direction. So let's look at a couple examples. We're going to try to find the magnitude and direction of a couple vectors. So we'll of course put it in component form first. So in this case, our vector, we're going over 1 and we're going down 3. So 1, -3 is our vector. So remember, the magnitude is this distance here. In this case, it's u. So the magnitude squared is equal to the x component squared plus the y component squared. So the magnitude squared is going to equal 1 plus 9, which is 10. And then I can simply take the square root. So the magnitude is going to be the square root of 10. So that vector has a length of the square root of 10. Now, as far as the angle and the direction, it goes all the way around here. So we know it's an angle somewhere between 270 degrees and 360 degrees. So what I'll do first is I'll take my reference angle, which is the inverse tangent of y over x, so -3 over 1. So you could put that into your calculator. Just make sure if you are using a TI calculator or Desmos, you're making sure it's in degree mode. So when I put this in the calculator, I get -71.6. I'll go to the nearest 10. Now, if you really want to talk about the reference angle, we can just assume the reference angle is positive. So that's going to be the angle between the terminal ray, the vector, and the x-axis. Now that's obviously not the angle we want because our angle is somewhere between 270 and 360. So in this case, what we'll do is our angle is going to be the total 360, but then we'll back it up to our vector. So 360 minus 71.6. So 360 minus 71.6 will give us our direction of our angle, which is 288.4 degrees. So this vector has a length of radical 10 and an angle of 288.4 for its direction. Okay, let's look at another example. So here is this vector. So this is again the one we talked about earlier where the y component is going down 5 and the x component is going back 8. So this is vector -8, -5. So the magnitude of this vector, this is vector v. Remember the magnitude squared equals the x component squared plus the y component squared, just a simple Pythagorean theorem. So the magnitude of this vector, the length, is going to be 64 plus 25. So the magnitude squared is 89. So we'll simply take the square root. So the magnitude is going to be the square root of 89. So this vector is square root of 89 units long. That's its magnitude. Let's talk about its direction. Now, if I were to draw this vector in position form with -8, -5, it would look something like this. So its angle is going to be somewhere between 180 and 270, or pi and 3 pi over 2. So we'll use that formula again. The reference angle is going to be the inverse tangent of y over x, which is going to be 5/8. So if I figure out what the inverse tangent of 5/8 is, I get 32.00. So we'll say it's 32.0. Now that's the reference angle. So that's the angle between the x-axis and the vector. So this angle is 32.0. So to get the whole angle, in this case, we'll take 180 plus that angle. So our total angle will be 180 plus the reference angle. So just like with the trig equations, you have to kind of use a little bit of geometric knowledge to figure out what these are. So there's our magnitude of our vector, and there's our direction. All used with that Pythagorean theorem formula, and the reference angle being the arctangent, inverse tangent. Okay, we can also look at taking a scalar multiple times a vector. So if we have vector u, then we can multiply that vector by a, or any number a, right? So if we have some vector, let's say u is equal to vector u sub x, u sub y, then if I want to find a times u, where a is just some number, then all I have to do is multiply a times the x component and a times the y component. So, pretty simple. So we're just taking a number times a vector, or a scalar times a vector. So for example, if we have a equal to vector 3, 5, and I want the vector 1/3 a, this is really talking about 1/3 times vector 3, 5. So all I have to do this is I'll take 1/3 times 3, and I'll take 1/3 times 5. So really what this will do is this will shrink or extend your magnitude. So that's going to be 1, 5/3. So this is vector 1/3 a. So a is 3, 5 over 3 up 5. This one is much shorter, over 1 up 5/3. Now, once you have your new vector, you can simply, you can find magnitude, you can find direction, you can do all those things. So let's say we have vector b, which is 2i minus 5j. It says I want vector 3b. So the first thing I would do is I would figure out what vector 3b is. So I'm just going to multiply 3 times both of these components. So this will be 6i minus 15j. So if I think about what that looks like, it's over 6, and we're going down 15 all the way down here. We'll say that's 15-ish. So my vector is going to point to quadrant 4. This is important because when I'm trying to find the magnitude and direction, it says only magnitude, but we'll find this direction as well. The direction is going to be in quadrant 4. That will be important. So remember, the magnitude of vector 3b is just going to be equal to the sum of the squares of its components. So 6 squared plus 15 squared. So that's going to equal 36 plus 225. That equals 261. So then we can take the square root. So the magnitude of 3b is going to equal the square root of 261. Now, if I want the direction, again, remember the reference angle is going to be the inverse tan of y over x. So it's going to be the inverse tan of negative 15 over 6. So the inverse tan of negative 15 over 6 is going to give me negative 68.2. So as a reference angle, it's really 68.2. So that's going to be the angle between the vector and the x-axis. So it looks like this. So since our big directional red angle here is in quadrant 4, we're just going to take 360 and back it up by the reference angle. So our directional angle will be 360 minus 68.2. 360 minus 68.2 is 291.8. So there's our magnitude, and there's our direction, just as a bonus. So when you have a scalar, when you're multiplying it, it's just really multiplying that number to both parts of the vector, nothing else. Okay, we can also find component form of a vector given the direction and the magnitude. So if we're given a magnitude and a direction, an angle, our goal is to try to figure out what is the x component and what is the y component. So we're going to do this by kind of looking at a picture. So let's go ahead and look at a vector. So if this is my angle and this is my magnitude, is the length, then again I can form a right triangle, and my x component is right here and my y component is right here. So when we're trying to actually figure out what the x and y components are, we can actually use this right triangle. So remember, the angle here is going to be the same as the big angle except for a different sign, but the calculator will take that into consideration for us. So in this triangle, we know the sine is equal to the opposite side over the hypotenuse, which is the magnitude. So I can solve for that by just multiplying both sides by the magnitude. So the y component is always going to be the magnitude times the sine of your directional angle. In a similar fashion, we know the cosine of the angle is equal to the x component divided by the magnitude. So when I multiply both sides by the magnitude cosine of theta. So now we have these two formulas that are really, really nice. So if you have the magnitude and direction, you can just use these two formulas. So for example, if I want to find the component form of a vector with direction of 225 and magnitude of 10, I'm just trying to find the x component and the y component. So the x component is going to be the magnitude times the cosine of 225. And the y component is going to be the magnitude times the sine of 225. So if you want the exact values for these, you certainly can, because we know the cosine of 225 is negative radical 2 over 2. And the sine of 225 is negative radical 2 over 2. These are both from the unit circle. So this one would be negative 10 radical 2 over 2. And this one would be negative 10 radical 2 over 2. So if I simplified, my final answer would be negative 5 radical 2 and negative 5 radical 2. Now, if you wanted to put this in the calculator and get the decimal approximation, that is certainly okay. Just make sure when you're doing an assignment or an assessment that you look if it's looking for the exact value or if it's looking for an approximation. Obviously, only angles on the unit circle could I actually get the exact value. So hopefully this is helpful. Let me know if you have any questions.